Some atoms shouldn't exist, and yet you do. The universe doesn't make mistakes. Or so we're told. Every rule, every constant, every law of nature, etched in the silent fabric of space-time, obeyed without question, without exception. But what if, nestled inside that silence, was a contradiction, a whisper of something that shouldn't be there, something like you? Because the atoms that make up your body, the carbon in your cells, the oxygen in your lungs, the calcium in your bones, by all logical accounts, should never have existed at all. And yet, here you are, breathing, watching, thinking. The atoms survived, the rules were bent, the universe blinked, and we still don't know why. Let's rewind, back to the beginning. Not the beginning of your life, not even the beginning of Earth, but the true beginning, 13.8 billion years ago, when time itself flickered into existence. A blinding explosion, infinite density, zero time, the Big Bang. From nothing came everything, or at least the raw ingredients of everything: energy, expansion, chaos. And from that chaos, something else was born. Something tiny, elusive, incredibly strange. The first atom. It was hydrogen, one proton, one electron. That's it, the simplest thing in the universe. And somehow, the most persistent. Hydrogen was the first to form, and it's still the most abundant atom in the cosmos. But even that was a miracle. Because in the moments after the Big Bang, atoms weren't supposed to form at all. The universe was too hot, too dense, too violent. Particles smashed into each other with the fury of a collapsing star. Protons and neutrons couldn't hold hands for more than a breath before being ripped apart again. The odds of stable atoms emerging from that inferno? Slim. Infinitesimal. Impossible. But impossibility has never stopped the universe before. As the cosmos cooled, a narrow window opened, just wide enough for protons and neutrons to bond, just long enough for hydrogen and helium to form. And in that brief, quiet pause between chaos and collapse, the first real building blocks of matter snuck through. These atoms were fragile, alone, blind, but they were the beginning of everything: stars, planets, galaxies, you. And yet, not all atoms were so lucky. Some were stillborn. They formed, then unraveled instantly, like beryllium-8, an atom that exists for less than a trillionth of a second before it tears itself apart. Some atoms that we desperately need, like carbon, the atom that forms the backbone of every living thing, should have never formed at all. Without carbon, there is no DNA, no biology, no life. So how did carbon get here? Well, that's where the mystery deepens. Because carbon only exists thanks to a loophole in the laws of physics, a gap so precise, so fragile, that if it were off by just 1%, life would be impossible. And it gets weirder. The same Big Bang that birthed matter also birthed antimatter. And for every atom of matter, there should have been an atom of antimatter. Perfect symmetry. But when matter and antimatter collide, they annihilate each other in a burst of pure energy. If the universe had followed its own rules, all the atoms should have vanished, gone in a flash. A sterile universe, no stars, no planets, no people. But again, that didn't happen. Instead, somehow, there was a mistake. A rounding error in the cosmic ledger. For every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. That one extra, that unbalanced speck of imperfection, that's us, that's all of it. Everything you've ever seen, touched or loved, carved from the wreckage of a war between matter and its mirror. A war we still don't understand. The universe, it seems, is full of these impossibilities. Atoms that shouldn't exist. Rules that shouldn't be bendable. Events that shouldn't have happened. And yet, they did. And in their wake, something utterly unique appeared. Not just matter, not just stars, awareness. Over the next 90 minutes, we'll follow the trail of these impossible atoms, from the secrets of hydrogen and the miracle of carbon to quantum oddities and particles that defy the very physics meant to contain them. We'll uncover atoms that live for a trillionth of a second, atoms born in the hearts of dying stars, atoms that seem to know when they're being watched. And by the end of this journey, we'll return to one haunting question. If these atoms shouldn't exist, then why do they? And what does that say about you? We talk about atoms like we understand them, as if they're solid, tangible things, little marbles making up the fabric of reality. But that image, the neat, compact atom with electrons spinning around a nucleus like tiny planets around a sun, is a lie. A useful one, perhaps, but a lie all the same, because the truth is far stranger. An atom is not a thing. It is a field of probabilities, a haze of uncertainty, a ghost wrapped in math. The nucleus, the atom's dense central heart, is absurdly small. If an atom were the size of a football stadium, the nucleus would be a grain of rice at midfield. And the electrons? They wouldn't be whizzing around like orbiting moons. They'd be everywhere, nowhere, both at once. Electrons don't follow tracks. They don't have fixed positions. They exist as clouds, spreads of possibility. You can't point to where an electron is, only where it's likely to be, until you look. And when you look, the electron seems to decide where it should be. As if it knows. It gets worse. Because what we think of as solid matter is, in truth, mostly empty space. You've heard the statistic before. If you removed all the empty space inside atoms, the entire human race could fit inside a sugar cube. And yet you can't walk through walls. Why? Not because atoms are solid, but because of forces, invisible fields of repulsion, electrons resisting overlap, quantum rules preventing two particles from occupying the same space at the same time. In other words, you're not touching the world. You're hovering just above it, held back by invisible barriers. You've never truly touched anything. And yet, you feel the pressure. You feel weight, warmth, texture. Your entire experience of reality, touch, pressure, pain, is a translation, a trick of the brain, interpreting electric signals from atoms that never really collided. What then is real? This is the question that has haunted physics since its earliest days, because the closer we look at atoms, the more they dissolve, the more they blur and flicker, the more they reveal not certainty, but contradiction. Consider this. Atoms are made of protons, neutrons, and electrons, but protons and neutrons are themselves made of even smaller particles, quarks, bound together by gluons, held in place by forces so powerful and so poorly understood. We've named one of them the strong force, simply because it is. And yet, quarks have never been observed in isolation. No one has ever seen a lone quark drifting through space. They exist only in tightly bound groups. Why? We don't know. It's just how the universe works. It's almost as if the building blocks of reality are afraid to be alone. Then there's the question of mass. You might think atoms are heavy because of the stuff they're made of, but here's the twist. The actual mass of a proton isn't just the mass of its quarks. In fact, most of its mass comes from nothing, or rather, from the energy of the fields between the quarks, mass from motion, mass from interaction, from vibration. Which means atoms are not made of stuff, they are made of relationships. Everything you are, everything you see is the product of interaction, not substance, not particles, but the energy between them. You are made of forces, of fields, of movement frozen into form. That form, however, is not fixed. Atoms vibrate, they shift, they exist in constant motion even in objects that appear still. At room temperature, the atoms in your body vibrate billions of times per second. You are a symphony of motion, even at rest. This dance of vibration is what allows atoms to bond, to build, to break. It's what allows molecules to form, cells to function, brains to fire, and yet no single atom knows what it's doing. No electron chooses its path, no proton plans its behavior, but together, somehow, they create stars, rivers, snowflakes, language, consciousness. This is the paradox at the heart of existence. From simplicity, complexity, from randomness, order, from atoms with no awareness, the emergence of beings who ask why. But before we get to emergence, we must first understand how these atoms were even allowed to exist in the first place, because many of them, by all rights, should never have made it this far. We often think of atoms as inevitable, a given, as if, once the universe existed, atoms were a foregone conclusion. They weren't. In fact, their creation required conditions so specific, so precise, that even a tiny deviation would have rendered them impossible. Take hydrogen, for instance, the simplest atom, just one proton and one electron. You'd think it would be easy to make. But in the early universe, conditions had to be just right, not too hot, not too fast expanding, not too dense. Any faster and particles wouldn't collide, any slower, and they'd collapse into black holes before forming anything stable. The timing had to be perfect, and it was. But only for a moment. In that fleeting window, hydrogen was born. And from that one success, everything else could begin. Stars could form, gravity could gather clouds of hydrogen together, pressure could ignite fusion. And inside the first stars, new atoms, heavier atoms, could be forged. But not all atoms were so cooperative. Some defied formation, others crumbled as soon as they were made. Still others, like carbon, required loopholes in the laws of nature to even exist. It is to these rare, precious exceptions that we now turn, because it is in their unlikely stories that the mystery of existence deepens, and the impossible begins to look intentional. We are about to meet the first atom that truly shouldn't exist. An atom so unstable, so fragile that its existence opens more questions than it answers. And yet without it, you would not be here. It is time to meet beryllium-8. Some atoms are stable, some are dangerous. And then there's beryllium-8, an atom so unstable it seems custom-built not to exist. And yet, paradoxically, this atom's brief flicker of existence may have made everything else possible. Beryllium-8 lives on the edge of reality. It is created in stars, forged under unimaginable heat and pressure. But no sooner is it born than it begins to fall apart. Its lifespan? Roughly 1/4,000,000th of a second. That's a 1.0 times 10 to the -6 nanoseconds existence, so short that even light, the fastest thing in the universe, barely moves the width of a proton before beryllium-8 collapses back into nothingness. You could spend your entire life watching stars burn, and you'd never catch a glimpse of it. It's gone before it begins. So why does it matter? Because the universe needed beryllium-8 to pause, even for just that trillionth of a second. It needed a tiny, impossible window to remain open so that carbon, the backbone of every living organism, could form. Without that pause, you don't exist. Let's step back. Inside stars, atomic fusion acts like a cosmic forge. Lighter atoms are squeezed together under gravity, merging into heavier ones. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and onward up the periodic table. But the path from helium to carbon isn't straightforward. Two helium nuclei, also known as alpha particles, can fuse to form beryllium-8. But because beryllium-8 is wildly unstable, it breaks apart before anything else can happen. For millions of years, this posed a puzzle. Scientists understood the basics of stellar fusion, but not how carbon was being made. If beryllium-8 shattered too quickly, how did stars ever manage to build the carbon atoms that made life possible? The answer came in the form of one of the boldest predictions in the history of physics. In the 1950s, astrophysicist Fred Hoyle proposed something radical. He suggested that there must be a resonance, a specific energy level in carbon-12 that perfectly matched the combined energy of beryllium-8 and a third helium nucleus. In other words, Hoyle was saying, The universe had to cheat. For carbon to exist, nature needed to hold beryllium-8 together just long enough to slam in a third helium nucleus, creating a three-particle fusion process known as the triple alpha reaction. Hoyle had no experimental proof, just logic. He reasoned that if life exists, then carbon must be able to form. And if carbon forms, then there must be a precise energy level in the carbon nucleus that allows it. And he was right. When scientists checked the carbon atom structure, they found a resonance exactly where Hoyle said it would be. A 1 in a billion coincidence, or something deeper? That resonance level, the one Hoyle predicted, sits at just the right energy to catch beryllium-8 in its brief moment of almost existence, fusing it into carbon before it tears itself apart. If that resonance level were even slightly higher or lower, by just 1 part in 1,000, carbon wouldn't form. No carbon, no life, no plants, no animals, no people, no thought. The universe would be sterile. But that's not what happened. What happened was us. Fred Hoyle's discovery sent shockwaves through the scientific community because his logic had been backwards. Instead of deriving a prediction from equations, he had started with a philosophical assumption. Life exists, therefore the universe must be structured to allow it. That logic has a name, the anthropic principle. It's a dangerous idea, a seductive one. It suggests that the laws of physics may not be universal constants at all, but parameters fine-tuned for our existence. As if the universe isn't just capable of producing life, but designed to. Hoyle himself, though a lifelong atheist, was shaken by the implications. He once said, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics." The deeper scientists looked into atomic structure, the more fine-tuning they found. Carbon's resonance isn't the only anomaly. The precise masses of protons and neutrons, the strength of nuclear forces, the properties of fundamental constants, all balanced on a knife's edge. Too much gravity, and stars collapse before fusion begins. Too little, and stars never ignite. A slightly stronger strong force and atoms are too sticky. Hydrogen is unstable. A slightly weaker one, and atoms can't hold together at all. Every dial seems set just right. Too right. And all of it hinges on a single, absurdly unstable atom, beryllium-8, existing for just long enough to let something else happen. Just long enough to cheat death. Just long enough to create carbon. Just long enough to create you. This is the kind of secret that hides in plain sight. It's not poetic metaphor. It's physics. The atom that shouldn't exist did exist. Briefly, violently, miraculously. And in doing so, it cracked the door open for everything else to follow. So the question isn't just, how did it happen? The question is, why did it happen at all? Because when nature builds a system so precariously balanced, when the whole of biological life depends on the survival of a particle that vanishes almost before it appears, you're forced to wonder, was it all chance? Or is there something deeper written in the bones of the cosmos? Maybe, just maybe, atoms aren't the only thing that shouldn't exist. Maybe improbability is the only constant that ever really mattered. Every carbon atom in your body, every single one, was forged in the violent collapsing heart of a dying star. Your bones, your brain, your breath, all of it began as fire. To understand how this happened, we have to enter the one place in the universe where nature's most improbable experiments are conducted, the stellar core. A star is not a light bulb. It is not a ball of flame. It is a machine, a reactor, a crucible. At its core, gravity crushes matter inward with incredible force. Hydrogen atoms, drawn together by that relentless pressure, are slammed into each other with such intensity that their nuclei fuse. When they do, they release energy, pure, radiant energy, and that energy pushes back against the pull of gravity. For a time, the star is balanced, gravity pulling in, fusion pushing out, a stalemate made of fire. This is how stars live, but it is also how stars die. Because fusion is a thief, it transforms fuel into ash. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and so on, climbing the periodic ladder. But with each step, the fuel becomes harder to burn, the reactions more demanding, the elements heavier. Eventually the balance collapses, but before it does, in the star's final breath, something astonishing happens. Helium, the second lightest element, begins to fuse, not just once but twice, in rapid succession. 3 helium nuclei slamming together, caught in the momentary net of beryllium-8, create something new. Carbon-12. It's a process known as the triple alpha reaction, and it's one of the most delicate chains of cause and effect in the known universe. Because remember, helium nuclei don't want to stick together. Beryllium-8 shatters almost instantly. The only way this process works is if a third helium hits just right, just in time, to stabilize the reaction. There is no backup plan, no alternative pathway. Carbon doesn't form any other way, and yet stars do it, over and over again, across billions of galaxies, billions of years. The odds are ridiculous. And yet the stars are full of carbon. They make it, they burn it, they expel it in their death throes, massive luminous explosions called supernovae. When a massive star dies, it collapses inward. Pressure spikes, the core implodes, and then suddenly all that energy explodes outward in a final furious release. The star tears itself apart, hurling atoms into the void. Carbon, oxygen, iron, gold, uranium. A galaxy becomes a graveyard, but also a nursery, because those atoms don't vanish. They drift, they wander, they cling to dust, to gravity, to time. And eventually some of them gather again, into new stars, new planets, new chances. Your body contains around 10 octillion atoms. That's a 1 followed by 28 zeros, and most of them were formed inside stars that died long before the Earth was born. Your carbon may have come from one star, your oxygen from another, your calcium from yet another. You are, quite literally, a patchwork of ancient stellar deaths. We say we are made of stardust, but that's not poetry. It's not metaphor. It is fact. The atoms in your body were once forged in fire, then scattered, then gathered again into oceans, into trees, into animals, into people. The same carbon that runs through your blood may have once floated through the rings of Saturn. The same oxygen in your lungs may have once burned in the atmosphere of a dead world. And now, they are you. But we're not done yet, because carbon, for all its miraculous formation, is only one piece of the puzzle, a crucial one, but incomplete. Carbon makes complex molecules possible, chains, branches, rings. It allows for the chemistry of life. But without stability, those chains fall apart. Without oxygen, there's no combustion, no metabolism, no breath. Without calcium, your nerves don't fire, your bones don't form. Every atom has a role, a part to play. And all of them, every last one, were built on the same improbable stage. Fusion, fire, collapse, explosion. The universe is not a quiet place. It is an engine of destruction. But from that destruction, beauty arises. You are living proof. The beryllium-8 that shouldn't have lasted did. The carbon that shouldn't have formed did. The stars that shouldn't have burned long enough did. And somehow all of it found its way into you. What are the odds? Impossible. But then again, maybe that's just what reality is. An unbroken string of impossibilities that somehow keep happening. Carbon should not exist. We've said it before, but we need to say it again. Because the deeper we look into the numbers, the more improbable it becomes. At the center of this improbability is something called a resonance level, an energy state within the carbon-12 nucleus. Think of it like a hidden shelf, perfectly positioned for 3 helium nuclei to land on, momentarily align, and form something entirely new. Fred Hoyle predicted this energy level not by experiment, but by necessity. He didn't ask, what does physics allow? He asked, what must be true in order for life to exist? And then he went looking for it. The number he predicted was 7.65 million electron volts, a specific delicate energy state inside the carbon atom. And when physicists looked for it, they found it, exactly where Hoyle said it would be. This wasn't just luck, it was uncanny, because if that energy level had been off by even 1 part in 1,000, carbon would never form. Or it would break apart before bonding, or it would never bond again after forming once. No carbon means no life, full stop. We're not talking about chemistry here. We're talking about the architecture of the universe. A change so small, so minute, it defies intuition, and yet would result in a cosmos of lifeless dust. And that wasn't the only one. Physicists began to notice that other constants, the mass of the proton, the charge of the electron, the strength of gravity, the rate of cosmic expansion, were all perched on razor's edges. Change them ever so slightly, and the universe collapses before atoms can form, or expands too fast for stars to ignite, or traps all matter in black holes, or never makes anything more complex than hydrogen gas. This growing body of evidence began to feel intentional, or at least suspicious. It was as if someone had walked into a control room filled with dials, one for gravity, one for electromagnetism, one for nuclear force, and set each dial with surgical precision, knowing that the slightest misstep would break the machine. This idea, this eerie sense of balance, became known as fine-tuning. To some, it was evidence of design, a creator, a watchmaker setting the universe into motion. To others, it was proof of something more abstract, the anthropic principle. The notion that we can only observe this universe because it allows observers like us to exist. In other words, there may be countless universes, most of them sterile, broken, or empty, and we just happen to live in the one that works. But even this doesn't settle the discomfort, because whether it's a god, a multiverse, or blind luck, we're still left with the same haunting fact. Our existence hinges on a knife's edge, and carbon is just the beginning. Let's take a closer look. The strength of the strong nuclear force, for example, determines how tightly atomic nuclei are held together. If it were just 2% stronger, the universe would have no hydrogen, because all the hydrogen from the Big Bang would have fused into helium too quickly. No hydrogen means no stars like our sun, no water, no life. If it were 2% weaker, atomic nuclei wouldn't hold together at all. Protons and neutrons would fly apart. No stable elements, no chemistry, just a soup of particles, forever unbound. Then there's the electromagnetic force, which governs how electrons orbit nuclei. Alter its strength and atoms wouldn't form the complex structures needed for life. Or electrons would spiral into nuclei, or atoms would fly apart at the slightest touch. It goes on and on. The mass ratio between protons and electrons, the rate of cosmic inflation after the Big Bang, the temperature of nuclear fusion inside stars, each one had to fall into an impossibly narrow window, and all of them did. It's enough to make even hardened scientists pause, because in every direction the numbers seem to whisper, this shouldn't be here, and yet it is. You are. The more we learn about atoms, the more we realize they are not inevitable, they are not guaranteed. They are, in the deepest sense, contingent, dependent, precarious. It's as if the universe spent 13.8 billion years threading a cosmic needle, through the chaos of expansion, the heat of stars, the instability of rare particles, just to assemble the fragile matter we call home. And maybe that's all it is, a fluke, a cosmic accident. But what if it's not? What if the universe isn't just permitting life? What if it's inviting it? These are questions physics cannot answer, not yet, maybe not ever. But atoms do not lie. Their precision is undeniable, and their improbability is real. And somewhere in that improbability, floating inside the carbon atoms in your cells, is a story too strange to be coincidence, too precise to ignore. A story that started long before you were born, and that somehow needed you to finish it. The story of atoms isn't just about what was created, it's about what wasn't. Because for every atom that exists, there should have been one that didn't survive. At the moment of the Big Bang, the universe was a furnace of unimaginable heat and density. Energy surged through the void, giving birth to the most fundamental particles: quarks, electrons, photons, and something else. They're mirrors, antimatter. Every particle in existence has an opposite, a twin, same mass, same spin, but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy, gone, erased, as if neither had ever existed. And at the beginning, it should have been perfectly balanced. Every proton matched by an antiproton, every electron by a positron, matter and antimatter paired like dancers in a cosmic waltz, spinning into being, destined to cancel one another out. Which means the universe should have destroyed itself before it ever began. No stars, no galaxies, no carbon, no life. And yet, here you are.
Here we are.
That balance, perfect in theory, was violated. Somehow, for every billion antimatter particles, there were 1,000,000,001 matter particles. One extra, one mistake, one asymmetry in the mathematics of annihilation, and it changed everything. That one particle in a billion is the reason the universe has substance, the reason stars burn, the reason planets formed, the reason your body, your thoughts, your memories have mass, but no one knows why. The laws of physics, as we understand them, don't allow for this imbalance. There should be no bias, no favoritism. Matter and antimatter are supposed to be symmetrical, interchangeable. But something broke that symmetry. Something introduced a crack in the mirror. Physicists call this mystery baryon asymmetry, and it's one of the greatest unanswered questions in all of science. Every known process for creating particles, every collision, every fusion, every reaction, produces matter and antimatter in equal measure. So why is the universe made of matter? One hypothesis points to something called CP violation, a subtle violation of charge parity symmetry. In certain rare particle interactions, tiny differences have been observed between how matter and antimatter behave. These differences are minuscule, barely detectable, but they suggest that the laws of the universe may not be as symmetrical as we once believed. And yet, the known CP violations are far too weak to explain the overwhelming dominance of matter. They offer a clue, but not a solution. Other theories suggest the involvement of neutrinos, ghostly, nearly massless particles that pass through your body by the trillions every second. Some physicists believe neutrinos may be their own antiparticles, and that in the early universe their decays tipped the balance in favor of matter. Still others propose that the imbalance is a consequence of inflation, the rapid expansion of space in the first instant after the Big Bang, amplifying quantum fluctuations that favored matter by chance. And then there's the multiverse theory. If countless universes exist, each with different physical constants and initial conditions, then most of them would be lifeless. But a few, by sheer random chance, might get the settings just right. We live in one of those few, a statistical accident, an outlier that happened to roll the cosmic dice and win. But none of these theories are proven, none have closed the case. And so the question remains, suspended in silence: why is there something instead of nothing? Why wasn't the universe a flash of light and then eternal darkness? Why did matter win? There is a kind of unease that settles in when science runs out of answers, when logic breaks down and all that's left is a handful of improbable facts. This is one of those moments. Because the laws of physics tell us that you shouldn't exist, and yet you do. The hydrogen in your blood, the oxygen in your lungs, the calcium in your bones, all of it descended from that 1,000,000,001st particle. The one that didn't vanish, the one that tipped the scale, the one that made a universe. And here's the strangest part. That particle could have been anywhere, in a galaxy far from ours, in a world that never formed, in the vacuum of deep space. But somehow, the atoms that survived became you. You are not just made of matter, you are made of victory. The tiniest, most improbable victory in the history of time. And the battle isn't over. Even now, the universe is still expanding, still cooling, still evolving. The atoms remain, but their future is uncertain. One day the stars will burn out, the galaxies will drift apart, and the last surviving atoms will fade into darkness. But before that happens, they will have danced, they will have dreamed, they will have become aware. And all because, somewhere at the beginning, the universe chose to keep one. Just one. Atoms are often thought of as stable, reliable things, the bricks of reality, predictable, trustworthy. But this illusion of order is just that, an illusion. Because some atoms break the rules, some atoms don't sit quietly in the periodic table. They decay, they shift, they cheat, they vanish, and sometimes they tunnel straight through walls. Let's start with a strange and unsettling phenomenon, quantum tunneling. Imagine a ball rolling toward a hill. If the ball doesn't have enough energy to climb over the hill, it stops. Simple enough. That's classical physics. But in the quantum world, the rules are different. In the quantum world, the ball doesn't need to climb the hill. It can disappear on one side and reappear on the other without ever crossing the top. This is quantum tunneling. A particle slipping through a barrier it shouldn't be able to pass. Not because it broke the laws of physics, but because it followed them. Tunneling is not rare, it's not theoretical, it happens all the time. It's the reason the sun shines. It's how radioactive elements decay. It's how life, your life, exists. Here's how it works. Inside atomic nuclei, protons and neutrons are held together by the strong nuclear force, a powerful but short-range interaction that binds them tightly. But in unstable atoms, this balance begins to crack. Take uranium-238. It has too many protons, too many neutrons. It's heavy, it's crowded. The forces holding it together start to fail. It wants to shed some of that weight. But the protons in the nucleus are positively charged, and so is the alpha particle, 2 protons and 2 neutrons. It wants to eject. Like charges repel, so to escape, the alpha particle would have to overcome a powerful electromagnetic barrier. Classically, that's impossible. The alpha particle doesn't have enough energy to climb out. But quantum mechanically, it doesn't have to. It just tunnels through. It appears outside the nucleus without ever crossing the barrier in the usual sense, and it happens with eerie consistency. Radioactive atoms decay on predictable timelines, as if chance itself were operating on a schedule. One atom might decay in a second, another waits 1,000 years. But across billions of atoms, the half-life, the time it takes for half of a sample to decay, remains astonishingly precise. It's randomness wrapped in law. This kind of behavior would be disturbing enough on its own, but it gets weirder. Some atoms are too stable, others too unstable. Nuclear physicists noticed that certain numbers of protons and neutrons, called magic numbers, made nuclei especially stable, like noble gases on the atomic scale. The magic numbers are 2, 8, 20, 28, 50, 82, and 126. Atoms with these numbers of protons or neutrons are more tightly bound, more resistant to decay. But why those numbers? Why that pattern? No one fully knows. It's like a hidden rhythm inside the atom, an invisible melody that only certain combinations of particles can hear. But the real magic may lie beyond what we've already seen. At the edges of the periodic table, past uranium and plutonium, lie the super-heavy elements. Most of them don't occur in nature. We've made them in labs, brief flashes of existence, lasting milliseconds or less. But some physicists believe that out there, in a region we haven't reached yet, there may exist an island of stability, an area of the periodic table where super-heavy elements are stable again, not for microseconds, but for hours, days, maybe even years. Elements with atomic numbers in the 100s or 130 that defy decay, that sit on new plateaus of balance. If we could find them or create them, they might unlock new forms of chemistry, new technologies, new materials beyond our imagination. But so far, we've only glimpsed the shoreline. The island remains hidden. Still, the idea haunts us. Because if nature repeats itself, if patterns emerge from chaos, then maybe atoms aren't done surprising us yet. Maybe there are still rules we haven't found, or better yet, rules waiting to be broken. Take metastable states, atoms that hover between being stable and not. They can remain in a kind of suspended animation for long periods, only to suddenly shift with no external trigger. Or isomeric transitions, where a nucleus rearranges its internal energy and jumps between states. It's like watching a mountain spontaneously rearrange itself into a valley. There are even atoms that, when decaying, produce neutrinos, particles so ghostly they barely interact with the rest of the universe. Trillions of them pass through you every second. They ignore atoms, ignore matter, ignore almost everything. And yet, their presence may have helped break the symmetry between matter and antimatter at the dawn of time. Everywhere we look in atomic physics, we find exceptions, anomalies, behavior that shouldn't happen, and yet does. Atoms tunnel. They decay without warning. They rearrange their internal structure. They stabilize in places we didn't expect. And they do all of it while following the most precise mathematical laws ever discovered. It's as if the universe allows cheating, so long as it's done according to the rule book. What does this tell us? That atoms are not simple, not settled. They are dynamic, rebellious, strange. They exist not in spite of the rules, but because of the peculiar, paradoxical nature of the rules themselves. Every rule has a loophole, every law has an exception, and reality, at its deepest level, is built not on certainty, but on probability. We don't live in a universe of perfect order. We live in a universe where the unlikely is not just possible, it's necessary. Atoms are born in fire, but the rarest, most precious ones, the ones that build planets, fuel our bodies and shape civilizations, are born in something far more violent: destruction. We tend to think of creation as a gentle process, life blooming, stars shining, worlds forming. But the universe doesn't work that way. The universe creates by tearing things apart. To build the elements that make up you, something else had to die. We've already seen how stars create carbon through fusion, how helium atoms are squeezed together to form heavier and heavier nuclei, step by step, inside stellar cores. But that only gets us so far. Fusion inside stars stops at iron. Why? Because fusing iron doesn't release energy, it consumes it. Once a star's core fills with iron, its engine fails. The balance between gravity pulling inward and pressure pushing outward breaks down. The star collapses. In that final moment, gravity wins. The core implodes, crushing atoms into neutrons. In a split second, the outer layers rebound against the collapsed core in a cataclysmic shockwave, a supernova. This is not an explosion, it's a detonation. A star 1,000,000 times the mass of Earth tearing itself to pieces. In the heart of that explosion, temperatures spike to billions of degrees, neutrons flood the wreckage, and for just a few seconds the conditions are perfect for something extraordinary to happen. The R process begins. The rapid neutron capture process is the most intense atomic assembly line in the universe. Neutrons slam into atomic nuclei faster than they can decay, building up heavier and heavier elements, gold, platinum, thorium, uranium, all in the blink of an eye. The atoms formed in this cosmic storm are unstable, exotic, rare, but some of them survive. They cool, they drift, they seed the galaxy with new material, and when those atoms find their way into planets and into living systems, they become part of something far more unlikely. They become part of you. You have atoms in your body that were forged in supernovae, in the last breath of stars that died before the Earth was born. You carry pieces of the dead. But supernovae aren't the only crucibles of creation. There is one event more violent, more rare, more powerful, the collision of two neutron stars. These are the dense, collapsed cores of massive stars. They're so compact that a single teaspoon of neutron star material weighs as much as a mountain. When two of these cosmic wrecking balls spiral into each other, They unleash a force that shakes the fabric of space itself. In 2017, we watched it happen. For the first time in human history, we detected the light and gravitational waves from two neutron stars colliding in a galaxy 130 million light-years away. The explosion was visible across the electromagnetic spectrum: X-rays, gamma rays, ultraviolet, infrared, and more. What we saw was extraordinary. The collision didn't just release energy, it created elements. Astronomers identified the fingerprints of newly formed gold and platinum in the aftermath. In a matter of seconds, more gold was created than exists in the entire solar system. That ring on your finger? It may have come from a neutron star collision. The uranium in the Earth's crust, born from the same violence. The atoms in your blood, iron, copper, zinc, were formed from fusion and decay, forged in layers of creation and collapse going back billions of years. Every piece of you has a history older than humanity, older than Earth, older than time as we know it. And here's the most humbling part. Those atoms didn't choose to become you. They weren't waiting. They weren't aware. They drifted. For eons, through space, through lightless voids, across frozen gas clouds and stellar winds, until eventually, inevitably, gravity did what it always does. It gathered the dust, formed a star, formed a planet, formed oceans, formed cells. And now, they think, they speak, they watch videos about themselves. This is not the destiny of atoms, it's their mutation, their aberration, their miracle. Because the universe doesn't need consciousness, it doesn't require minds or meaning, and yet, here you are. Every atom in your body came from a star, and the rarest ones, those forged in chaos, now live on as memory, as music, as thought. Creation through destruction, order born of collapse. In a universe governed by entropy, where everything moves toward decay, the brief flicker of organization, of structure, of life, is the greatest mystery of all. And it all comes down to atoms that should never have formed. Carbon in a dying star, gold in a neutron storm, iron in your blood, impossible matter from impossible events. And yet, here it is. Here you are. Atoms aren't just strange, they're watching. It sounds absurd, impossible, like something pulled from a sci-fi novel or a late-night thought spiral. But the more we study atoms, the more we discover something deeply unsettling. They change when we look at them. This isn't poetry. This is the foundation of quantum mechanics, and it begins with one of the most famous experiments in scientific history, the double-slit experiment. Imagine a wall with two vertical slits, and behind it, a screen that records impacts. You fire particles, electrons say, through the slits, one at a time. What you expect? Two neat lines on the screen matching the slits. What you get? An interference pattern, a wave-like distribution with bright and dark bands. The electrons don't behave like tiny bullets, they act like waves, waves that interfere with themselves, as if each electron somehow goes through both slits at the same time. This already defies common sense, but it gets worse. Now you place detectors at the slits to see which one the electron actually goes through. Suddenly, the interference pattern disappears. The electrons stop behaving like waves and start behaving like particles again. Two bands, no interference, just like you expected in the first place. But why? What changed? Nothing except your observation. Simply knowing which slit the electron passes through is enough to collapse the wave function, the mathematical description of all the possible states the electron could be in. Observation forces the atom to make a decision. Before the measurement, it's in a superposition, a blur of possibilities. After the measurement, it's something definite. This is called the observer effect, and it's not just limited to slits and screens. It's fundamental to quantum reality. Atoms exist in multiple potential states, all at once, until you interact with them, until you ask the universe a question, then it answers. What does that mean? Does the atom know it's being observed? Not in the conscious sense, but it reacts. It behaves differently based on your interaction with it. This raises an uncomfortable idea, that the act of observation is not passive, it's participatory. The observer isn't separate from the system. The observer defines the system. You can't just sit back and watch the universe, because by watching, you are changing it. Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that the wave function, the cloud of all possible outcomes, has no reality until it is observed. That possibility itself is the only thing that exists until observation forces one path to become real. Others, like the many worlds interpretation, propose that all outcomes happen, but in separate, parallel universes. The universe splits endlessly every time a quantum decision is made. In one world, the electron went through the left slit. In another, it went through the right. In another, it interfered with itself. In another, it vanished entirely. Every possible outcome realized. But no matter which interpretation you accept, they all share one eerie conclusion. There is no objective reality. Not at the quantum level, not in the world of atoms. There is only interaction, and interaction means involvement. It means you. This isn't some mystical claim. It's not consciousness creating reality. It's simply the fact that quantum systems evolve differently when measured. Measurement requires interaction. Interaction changes the system. But then, what is a measurement? A photon bouncing off an electron? A detector registering a blip? A human eye seeing a flash of light? At what point does a quantum event become real? When does probability become fact? No one knows. And that's the unsettling truth. We've mastered the equations. We can predict outcomes with stunning accuracy. Quantum mechanics powers your phone, your GPS, your computer. But we still don't know what it means. We don't know why atoms behave this way. We don't know what reality is when no one is watching. Does a tree fall in a forest if no one is there to hear it? Quantum mechanics doesn't answer that question. It asks it, at a subatomic level, 1 trillion times a second, inside every atom in your body. Reality is not fixed, it is fluid, contextual, and atoms are the shapeshifters at its core. They're not solid, they're not certain, they are probabilities, frozen only when we reach out and try to hold them still. And in that moment, brief as it is, they tell us a truth far stranger than we ever imagined. That the universe is not simply observed, it is co-created. You are not just made of atoms, you are part of the process that makes atoms real. Every atom in your body has a story, and none of those stories make any sense. They've been through stars, explosions, collisions, waves of light and fields of force. They've been born, destroyed, reborn again, and eventually, against all odds, they became you. But what does that really mean? It means that your body is not a structure, it's an event, a momentary convergence of ancient particles held together by chemistry, heat, and intention. You are made of atoms that were once scattered across the galaxy, hydrogen forged in the Big Bang, carbon from the hearts of stars, iron from supernovae, calcium and phosphorus fused in stellar furnaces, trace elements born in neutron star collisions that predate our sun. Your body is built from stardust, held together in a temporary truce, pulsing with energy. A self-organizing arrangement of atoms that somehow became aware of itself. Atoms don't know they're alive. They don't think, they don't dream. And yet, when arranged just right, they do. So let's zoom in. Inside your bloodstream, there are red blood cells carrying oxygen, an element produced in the final stages of stellar fusion. That oxygen binds with hemoglobin, a protein whose atoms form complex spirals and folds more intricate than anything we've ever engineered. That hemoglobin moves through arteries lined with smooth muscle, tissue woven from carbon, nitrogen, and hydrogen, molecules that would fly apart in any other context. Your brain contains about 86 billion neurons, each firing tiny electrical signals powered by sodium, potassium, and calcium ions, particles that obey quantum mechanics as precisely as any experiment ever performed. Every second, your body performs trillions of chemical reactions, each one involving atoms doing what atoms do, bonding, vibrating, repelling, attracting. But somehow the whole is greater than the sum of its parts. You aren't just atoms. You are arrangement. You are structure. You are pattern. What's astonishing isn't that atoms formed your body. What's astonishing is that your body knows it. That's the paradox, the miracle, the insult to logic. The particles themselves are blind. They follow rules. They don't understand. They don't question. But the arrangement they've formed in you is asking questions. Watching this, thinking, feeling, wondering. The same atoms that once floated aimlessly in interstellar space are now holding memories. Regret, joy, fear, love. The hydrogen in your DNA might once have drifted through a gas cloud near Alpha Centauri. The calcium in your teeth may have been part of a planet that burned long before Earth existed. The iron in your blood may have fallen to the surface of a dead star, then been scattered by a solar wind, only to be pulled into a growing dust disk that became this world. And now, those atoms are you, but not forever. Because this arrangement is temporary. Your atoms don't belong to you, they're just visiting, borrowed from the universe for a brief moment, held together by biology and balance. When your body dies, those atoms won't disappear. They'll break apart, drift, combine with other things, be recycled. They'll become the soil, the air, the sea. They'll become part of plants, animals, other people. Eventually they may return to the stars. Eventually, they may become someone else. You've been here before, just not as you. And you'll be here again, not because of memory, not because of soul, but because atoms never truly vanish. They change forms, they keep going. You are not eternal, but your atoms are. And the question we keep circling is this: why this arrangement? Why did all these particles forged in chaos, scattered across time and space, come together in you right now? There is no answer. Or maybe the answer is the journey itself. Because every improbable fusion, every broken symmetry, every unstable isotope and violent collision, each of them built the scaffold for this moment. For you, right now, wondering where your atoms came from. It shouldn't have happened. It couldn't have happened, and yet, it did. You are not made of ordinary things. You are made of impossibility, of particles that shouldn't exist, arranged in a way that shouldn't work, in a universe that shouldn't have survived its own birth. And somehow those particles are thinking. Somehow those atoms are aware. Somehow the universe, which began as blind chaos, now sees itself in you. We've traced the path of atoms across space and time, from the fires of the Big Bang to the cores of dying stars, from chaos to chemistry, from randomness to thought. And now we reach the edge. Because for all the mysteries we've explored, there's one question more profound than any other. A question that sits beneath them all, waiting, watching, never quite answerable. Why is there something instead of nothing? It's a question that feels childish at first, naive, almost silly. But ask any physicist or philosopher and they'll tell you, it's the hardest question in existence because it challenges the very basis of reality itself. Let's step back. The atoms we're made of shouldn't exist. The stars that forged them shouldn't have lasted. The matter we see should have annihilated with antimatter long ago. And yet, here it all is. Some physicists believe this can be explained with mathematics, that the laws of quantum mechanics and general relativity, when properly understood, will show that the universe simply had to exist, that energy, space, and time are emergent properties of deeper, invisible fields, like the quantum vacuum, a sea of potential that can, under the right conditions, fluctuate into somethingness. In this view, the universe is not a miracle. It's a statistical inevitability, a quantum fluctuation that happened to last. Others turn to string theory, or its broader umbrella, M-theory, frameworks that propose the universe is not alone, but one of many, an uncountable number of parallel universes, each with different laws, constants, and particles. In most of them, nothing happens. In some, atoms exist, but never organize. In a rare few, stars form, planets, life. We exist in one of the rare ones, because of course we do. If we didn't, we wouldn't be here to ask the question. This is the anthropic principle, the idea that we shouldn't be surprised to find the universe hospitable to life, because if it weren't, there'd be no one around to notice. It sounds clever, maybe even satisfying, but it isn't. It doesn't explain anything. It just describes the rules of the game after they've already been written. It doesn't tell us where the game came from, because even if there are infinite universes, even if quantum mechanics demands something rather than nothing, we're still left with the question, why does anything exist at all? Why are there rules? Why are there particles? Why is there time? Why this? Some have turned to metaphysics, the idea that existence is fundamental, that non-existence was never an option, that there has always been something, that nothingness is a human concept, not a physical one, that a true void in which no laws, no logic, no possibility exists is not only empty, it's impossible. But that just raises more questions. If there has always been something, why this something? Why this strange balanced universe? Why these particles, these forces? Why atoms at all? Others invoke a creator, a designer, not out of religious tradition but out of sheer mathematical astonishment. Fred Hoyle, who discovered the resonance in carbon that makes life possible, once remarked that the odds of that resonance appearing by chance were so small, it was like a tornado assembling a jet from a junkyard. But again, that answer just moves the mystery. If the universe was designed, who designed the designer? What made the creator possible? What came before? Every answer leads to another question. Every explanation opens another door, and behind that door, more uncertainty. What's clear is that existence is not obvious. It's not expected. It's not something we should take for granted. It is fragile, specific, haunting, and atoms, simple, ancient, indifferent atoms, carry this burden silently. They obey rules they never wrote. They hold structures they cannot see. They form patterns they do not understand. But somehow those patterns become us. Beings who ask, who wonder, who long for answers in the dark. And maybe that's the point. Maybe the question matters more than the answer. Because to ask, why is there something instead of nothing, is to recognize in the deepest possible way that your existence is not guaranteed. It is not owed. It is not normal. It is the exception. And the atoms that make you are the proof. Not just because they're rare, not just because they're old, but because they weren't supposed to be here at all. The hydrogen that survived the Big Bang, the carbon that slipped through a resonance loophole, the matter that escaped annihilation by antimatter, it all comes together in a single haunting truth. The universe could have been nothing, but instead, it became you. Some atoms shouldn't exist. And yet, they do. That simple fact has unraveled everything we thought we knew about the universe. Because when we zoom in far enough, beneath cells, beneath molecules, beneath the illusion of solidity, we find something stranger than fiction. A world where particles flicker in and out of certainty, where forces hold matter together like spells, and where the very fabric of reality is stitched with exceptions. It turns out the universe doesn't run on common sense. It runs on improbability. And you are made of it. Every part of you, every breath, every heartbeat, every passing thought, none of it should be here. The carbon in your DNA was only made possible because a collapsing star bent the rules. The matter in your bones only exists because, for reasons still unknown, one extra particle survived a cosmic war with its perfect twin. The universe chose imbalance. The atoms chose to dance. And from that chaos came consciousness. You are the aftershock of an impossible equation, a living arrangement of particles that should have cancelled each other out before the first second of time had even finished ticking, but they didn't. Instead, they did something unprecedented. They stayed, they organized, they remembered. Atoms don't have purpose, they don't have wants. But when they come together in just the right way, they begin to resemble something with purpose. They begin to build structures. Those structures form systems. Those systems develop feedback, complexity, awareness. Eventually, one arrangement of atoms, just one, looked up at the night sky and realized, I'm made of that. Imagine the odds. Out of every possible arrangement of matter, every random collision of dust and gas and force, you ended up here, watching this, thinking about atoms, thinking about yourself. You are not made of stars. You are not made of dust. You are made of questions. The hydrogen in your body has never aged. It is nearly as old as time itself. It was born when the universe was barely seconds old. It has passed through stars and gas clouds and oceans and organisms, drifting endlessly until it found its way into you. And still, it isn't done. Because when you're gone, when this current arrangement of matter no longer holds, those atoms will keep going. They'll scatter, reassemble, become something else. A leaf, a mountain, a drop of rain, another person. They don't care what they become. But you do, because somewhere in all of this, somewhere between the birth of the cosmos and the firing of your neurons, meaning emerged. We don't know how, we don't know why, but we know it's real. Because you've felt it, you've loved, you've feared, you've mourned and hoped and wondered. You've asked questions about your place in this enormous, cold, beautiful machine, and whether there's more. What does it mean to be made of atoms that shouldn't exist? It means you're not a fluke. You're not an accident. You're not background noise in an uncaring cosmos. You are the universe, assembled, however briefly, into something that can notice itself. And isn't that enough? We spend so much time asking for purpose, for proof, for clarity. But maybe the miracle isn't in the answers. Maybe it's in the fact that we can ask the questions at all. Atoms are not supposed to think, or care, or dream. But here we are. Dreaming anyway. You exist on a knife's edge of impossibility. You were born from particles that broke the rules. That cheated destruction, that tunneled through walls and survived the end of stars, that refused to vanish. And maybe that's what you're doing too. Refusing to vanish. Refusing to be silent, refusing to accept that this was all for nothing. Because it wasn't. You are here. That alone is enough to change everything. And so we return to the beginning, to the question that started all of this. Why do some atoms exist when by every measure they shouldn't? Maybe it's not the atoms that matter. Maybe it's what they become. Maybe it was never about protons and neutrons. Maybe it was always about this moment, this fleeting, impossible intersection of consciousness and curiosity and wonder. Maybe the real miracle isn't that the atoms exist. Maybe it's that you do, and that you care enough to ask why. Some atoms shouldn't exist, but somehow they do, and that, perhaps, is the most beautiful impossibility of all. Thank you for joining us on this extraordinary journey through the cosmos, here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.